Good morning, class. The session is being recorded. Again, for privacy issue, make sure audio video is completely muted. Don't put anything in the chat. You can even change your name to your initials. At the end, for the roll sheet, you are asked to put it back when we are done with the recording. In the meantime, if you have a question, you're more than welcome to ask, or if you want to participate, understand this is being recorded and posted for everyone. So we are looking at exam 2 review, which covers section 3.2 to 3.5. We have a lot of formulas as far as logarithmic properties are concerned. We have seen this stuff in intermediate algebra, then in college algebra, and then in, let me just get rid of this, pre-calculus. And we use this, one of them, to show the derivative of a to the power of x, if you recall. So it's extremely important for everybody to know the basic logarithmic rules. More is coming your way. So I hope you're very comfortable with those. So just review them. As far as the exam is concerned, we are dealing with tons and tons of differentiation formulas. I hope everybody is comfortable with those. Having said that, we are going to look at some of the examples we've seen before, and some of the examples I picked up from the mixed derivative practice test. So let's see what happens. To refresh everyone's memory, first and foremost, you are going to simplify this. And then the derivative is very simple. Okay, if you want to differentiate this, f prime is 2 over 9 times negative 4 x to the power of negative 4 minus 1, which is minus 5. And you rewrite it as such. This is your final answer. I hope you remember that. Anytime you have a fractional expression, can I simplify it? So you make up two fractions, and now the derivative is just minus 7. You don't have to do much. Okay, everybody? In the case of an exponential function, I was just going over the logarithmic properties. The derivative is always itself. And then there is more to it. So if the base is e, the answer is e to the power of x. If it's not, then you have to tag along the natural log. If the exponent is x, you're done, like here. Okay. But if the exponent is a function of x, you also need the derivative of that by the chain rule. So this is from logarithmic rules. This is from the chain rule. For example, if you have 2 to the power of 7x, okay, so we need 2 to the power of 7x. By logarithmic rules, we need natural log of the base because the base is not e, so times ln2. And by the chain rule, the exponent is not x, the derivative of that, which is 7. Okay, so the function itself, and then ln2, and then number 7, and you rewrite it, and you're done. Okay, everybody? Here's the next one. Now, we had seen something similar to that when I dealt with sine, and I think this really helps understand the concept of a chain rule, okay? And the derivative of f of g is f prime of g of x. So you need to know what is f, what is the shell function, the outer function, the main function, if you will. So in this case, it's cosine. So you differentiate the cosine. So let's just do this together. So first, understand its cosine. So y prime is negative sine. But anytime you have a sinusoidal function, you have to write the argument. So you need the argument. And then 2x, the derivative is 2. This is the chain rule, everybody. This is the chain rule. You just rewrite that. This one, perhaps if we write it as cosine to the second power. And now we use the extended power rule. N or 2 sits in front. Cosine to the power of n minus 1, or simply 1. And then g prime of x, this is g, right? The derivative of cosine, which is negative sine. Let's just write that. In other words, y prime is 2 cosine x to the power of 1, I just leave it as cosine x. And then the derivative of cosine is negative sine, and we put the whole thing together. Okay. The next one, again, you're looking at cosine. So y prime gives you what? Negative sine. Negative sine of what? Whatever the argument is, you write it. Now, by the chain rule, we need g prime of x. X squared gives you 2x. And you put everything together in a proper manner, and you're done. This is the chain rule class. Okay. Again, let me write this as sine of 8x to the second power. And so we are using the extended power rule. 2 sits in front, sine 8x. Let's just write that. So we get y prime to the exponent becomes the coefficient. Sine 8x. I don't have to write to the power of 1, but let me write it just on purpose so you see what's going on. Now, what is the derivative of sine is cosine. Cosine of what? Whatever it is, 8x. And because it's not x, you need the derivative of this. Again, this is using the chain rule again, class. So actually, let me just erase this so you can see that. Okay, so let's just quickly recap. Two sits in front, sine to the power of 1, the derivative of cosine, but remember, cosine of what? Cosine of x, you're done. But cosine of 8x, you're not done. Cosine 8x, and then the derivative of 8x is 8. You put them together. This was discussed in the previous page. First, this is the product of 3x and 3 to the power of x. So this simply gives you number 3 times the second one. But the second one was discussed in the previous page. The answer to 3 to the power of x is 3 to the power of x. The base is e, you're done. The base is not e times ln 3. I put it in this format, ln a, doesn't matter, whatever the base might be. I think I put ln b in the previous page. So the derivative of 3 to the power of x is 3 to the power of x, then times ln 3. And then by the product rule times 3x. Okay, so let me just write it in the following manner. So let's say this is the f function, and this is the g function. So this is f prime g. Okay, let me just write that top of it. F prime g plus this whole thing is g prime f. Okay, everybody? Now, let's see how else we can write this. So I'm going to look at the first piece and say this, I can write 3 to the power of x plus 1. Why is that? Because the exponent on this is 1. So 1 plus x or x plus 1. And I hope you see the same thing happens here. This one and this one give us the same thing. And then what is left is ln 3 times x So you can say ln 3 times x. I don't want to put the x after ln 3 because one may think it's ln 3x. And now you factor out the 3 to the power of x plus 1. Okay, everybody? You can factor it out. I hope it's clear. Here's the next one. We are dealing with the product rule again. This is the f function. This is the g function, and we are using the product rule. So the derivative of x to the power of 4 is 4x cubed times e to the power of 2x. The derivative of e to the power of 2x is itself times 2 times x to the power of 4. Okay, I hope everybody's comfortable with the concept. So the derivative of x to the power of 4 is 4x cubed, okay? And the derivative of e to the power of 2x is these two pieces. You're done. Now do the algebra. What's in common? I see number 4, I see number 2, so 2 is in common. I see x cubed, I see x to the power of 4. So let me just write that for you. Between 4 and 2, we choose 2. X cubed, x to the power of 4, we choose the smaller exponent. And of course, e to the power of 2x, and just whatever is left, you put it in there, which is 2 plus x. I hope you see that, everybody. Okay, 2 plus x. So what's going on here? Again, the product rule. So we are looking at the product of 9x and x minus 1 to the power of 4. So 9x simply gives you 9. So you times this one. What about this one? 4 times the parentheses to the power of 1 less, that means 3. And then the derivative of the inside happened to be 1. The derivative of the parentheses is just 1. By the product rule times 9x. So let me just write it in this manner. If we say this is f, then this is f prime. Okay. If we say this is g, okay, then this is g. This is g prime. This is f. And basically you have to factor out what you can. So let's just quickly show you what's in common. 9 is in common. X minus 1 is in common. But remember, this has exponent 4. This has exponent 3. We go with the smaller of the two exponents. Okay. Now this one, basically you compare it to this one or you divide. You get x minus 1. The second one, let me use a different color. When you compare this one to this one, that means you divide, the 9 goes away, the x minus 1 cubed goes away. So what is left? Number 4 is there and x is there. X and 4x, they add up to 5x. And that's your final answer, everybody. That's your final answer. Okay. Okay. Anytime we have a fractional expression, we are looking to see if it's possible to simplify. This gives you x. This gives you 4. So that's the first thing you need to do. This is one of those questions on mixed derivative practice. And now it's a simple case of the extended power rule. This sits in front, then the same thing to the power of 5. Now the derivative of the inside happened to be 1. So g prime, so n, 6. G of x is x plus 4 to the power of n minus 1, that means 5. G prime happened to be 1, so times 1, you don't have to write, okay? So it's really times 1. It's a good practice to remember it's there. And you can always write it and then rewrite the answer because you don't want to take a chance. If it were anything other than that, let's say it was 2x plus 4, then you would need times 2, okay, class? Can I simplify that? That is the question you should always ask. The answer is no. So let's go with the extended power. So 3 sits in front. Same thing to the power of 2. Now g prime of x now requires the quotient rule. So that's why it's a combination of the chain rule or the extended power rule with what? The quotient rule. So one more time, 3 sits in front, the same thing to the power of 2. Let's differentiate this. This becomes 4 times 2x minus 9, okay, f prime g, minus g prime. The derivative of the bottom is 2 times 4x over 2x minus 9 squared. So this is your first and only calculus step. The rest is simplification that we are going to do in a moment. Okay, so what I want to do, first I want to write this. Okay, so I hope everybody is comfortable with this. Okay, we are just using the chain rule in conjunction with the quotient rule. So this becomes 8x, everybody, minus 36 minus 8x. We can drop this. Now, again, I want to take one more step, class, because I don't want anybody to make a mistake. So we are going to write this as 3 times. Now, the first parenthesis, I'm going to write it as 4x squared over 2x minus 9 squared. The first parenthesis. The second parenthesis, the numerator is left with negative 36, and the denominator is 2x minus 9 squared. The only reason I did that, because I want you to see what the result is, because really the denominator is 2x minus 9 squared and squared. 2 plus 2 is 4. You could see that here, but in case. Now, what is the numerator? Now, what is left in the numerator is the product of 3, 16x squared, and negative 36. The denominator, 2x minus 9 to the power of 4. When we multiply number 3 and 16 and negative 36, we get minus 1728, and that's x squared. The denominator, the exponents add up. Okay. Let's do this. Again, can we simplify? The answer is no. Let's differentiate using the quotient rule. In fact, in conjunction with the chain rule. So cosine gives you negative sine, everybody. So negative sine 5t and then times 5. Negative sine 5t times 5. Then times 5t. Let me just write the numerator because I want to make sure we have that. So we have negative, okay, sine 5t times 5, and then times the denominator 5t right there, prime g. Now minus g prime, which is 5 times cosine 5t over the bottom squared, or 5t squared, or 25t squared. This is 5t quantity squared. Practically, you're done. I hope you see that the numerator, you can take out a common factor of -5. Okay, because you can take out the negative and then 5. So what you're left with is 5t. There is a t here, don't miss that. 5t sine 5t. And this one, basically -5 is gone, and what is left is cosine 5t. And now this 5 cancels out this 25. Negative remains, everything else remains, and this changes to 5. And you're done. Again, I put it in a different color to make sure everybody can see it is there, it's not going anywhere. Okay. Now, anytime you have a fractional expression, you want to ask yourself, can I simplify it? Now, one thing that actually helps is that simplification means, do I have a factor of x plus 3 in the numerator? So even if you can factor the top but doesn't have a factor of x plus 3, doesn't have. So look for a factor of x plus 3. It happened to have it. If it doesn't have it, you have to go with the quotient rule. So x plus 3 cancels out. The answer is 2x plus 3, and the answer is simply 2. It's that simple. So your algebraic technique can help a lot. It's all about algebra, everybody. It's all about algebra. The growth in world population in millions, so pay attention to that, is estimated as follows. It is the number of years since 1960. We want to find the instantaneous rate of change for the year 2015. First of all, the moment you hear instantaneous rate, that means differentiation. So you need to differentiate and then figure out what's going on with 2015. So first, let's differentiate, which gives you 3,100 times the same thing, e to the power 0.01660, and then by the chain rule times the derivative of the exponent, which is 0.0166. Okay, everybody? And the product of these two gives you that. Now, in the year 2015, it is the number of years since 1960. For example, the year 2000 means 40 years later, just for the sake of argument. The year 2015 means 55 years later. Okay, class? So we are going to replace that and use a calculator, write the answer, and what it means. Okay, so 128.2273. Why millions people? Let's go back to this. That's why. And also, let's rewrite this actually as dp dt. The reason I want you to see it in this format, because I want you to be very comfortable as to how we arrive at the units of the population, change in population, millions of people, the units of time, whatever that happened to be, okay, that means years, right? So million people per year. What does it mean? That means in the year 2015 or on the year or after the year 2015, the population is increasing because it's a positive value, increasing by 128 million, roughly, million people per year. The population is increasing, okay? By this much, because it's positive. Okay. We did a similar question to this. It's not, okay, the length of a growing Tasmanian devil. Tasmanian devil is estimated by this function. L is a function, okay, L is a function of W. W is in kilograms, okay, L is in millimeters. Okay. And its weight can be estimated by W of t, where t is its age in weeks, okay? How fast is the length of a 30-week old Tasmanian devil changing? Okay. So basically, we want to use this formula. They're not asking to calculate certain pieces, you know, for example, the length or the weight after 30 weeks, although we may need it. So I hope you realize how we are going to do that. We did this before. So we want the L dt, and so we write the L, and then we write the dt in between. And what goes in between? Class, L is a function of W. So W goes in between. I hope you see that. Take a look at this one. So you need dW. Okay. So that's the idea, how we arrive at this. Now, the next thing is, okay, what is dLdW? 2.265 times the exponent. Again, don't be, you know, because the numbers are a little bit involved, don't be afraid of them. I mean, assume this is 5. So this times 5, okay? And then W to the power of the same thing minus 1, which becomes 4. But of course, it's not 5. So it's a little bit nasty, big deal, okay? So 2.265 times 2.543, W to the power of 1 has to be subtracted from this, okay? 1.543. dW dt is just 0.18. The derivative of this one with respect to time is only 0.18. And so multiplication of this number and this number and this number will result in this number. Again, I'm showing a lot of decimals. You really don't need that many because everything is an estimate, but just in case. Notice this is a function of W only. Now, if we were dealing with the function, we were interested in finding dl dt as a function of t, we must replace the W with this, and that would be the end of the story. However, we want to see how fast the length is changing. You don't even have to change that. Just calculate the W, okay? So W is 0.125 plus 0.18 times t, which is 30, okay? So that means 5.525. You can plug it in here. I mean, I just have calculated also the length. You really don't need that. The reason you don't, because this is not involved with that, okay? But in case it was, you could use that. Or in case the question is that, what is the length of a 30-week-old Tasmanian devil? That would be the length, but this is the change. So now we plug in. And when we plug in, we replace the W with 5.525, resulting in this number, almost 14.5 millimeters per week. That means the 30-week Tasmanian devil is growing, is increasing in length on week 30 or after week 30 by this much. 14.5, let's say, millimeters per week. Again, units of dl over dt. Do you see that? dl, millimeters, dt in weeks. Here's the second method. We could have found this as a function of t by replacing this w with this function. Okay, everybody? And now, if we go with that, how do you differentiate this? This number times the exponent times this to the power of the exponent minus 1. And then by the chain rule, the derivative of this is 0.18. I hope you see that, class. Okay. So I'm going to write that in case, then it would become the LDT or L prime of t is this number times the exponent, this number, times the same thing to the power of 1.543 times the derivative of the inside the parentheses is 0.18. And the product of those three numbers become this. What numbers? This number 2.265, this number 2.543, and this number 0.8. And if you multiply those three, you get this one. We did that here. Okay. So again, pretty straightforward. I'm going to remind you of what we did here. Basically, peaks and valleys corresponds to slope being 0, they correspond to 0. If it's decreasing, f prime is negative and it's below the x-axis. If it's increasing, f prime is positive and is above the x-axis. This is how you graph things. And corner points, they result in a hole because it's not differentiable. The way we did that, just to refresh your memory, we would find the pairs here, calculate the slope. If you just look at this one and never mind the rest, when you calculate the slope for this line segment, whatever it is, a horizontal line would be the answer. And you do the same thing for each and every one of them. So first, we have the pairs, we calculate the slopes. There are 4 line segments, 4 different slopes. So from here to here, that means look at this point, that gives you a hole, and then the line y equals -1/2, it stops here. This one goes from here, which is -1 to 0, and so on and so forth. I hope you remember this. We did that, okay, everybody? Very straightforward. So drawing and sketching the graph of the derivative function. Very straightforward. Okay. Find an equation of a tangent line to the graph of this function. We've seen it many times. You need a pair, you plug in. 4 squared, 16 minus, this is 12, this is 1 minus 13, so that gives you 4 and 3. Take a derivative and plug in. When you plug in, that gives you the slope. So you have the pair, you have the slope. I hope you remember this question when we did that last week. So y minus y1 is m times x minus x sub 1. So here's your pair, 4, 3, and here's your slope. Plug in to the math. This differentiation, we did that. Again, I hope you remember that. We changed this to x to the power of 1/2. So we can distribute, and now we use the power rule on that. Okay, we use the power rule. That means 3/2 sits in front, x to the power of 1/2 plus 5. And that's it. You just change this to square root of x. So that's how you differentiate. The point being, there are a lot of algebraic steps that we need to be worried about. All right. Again, we're going to change this. I hope you remember this question. If you put a raised dot in between, you're looking at the product rule. I hope you remember that. So this gives you 1/2 x to the power of -1/2 times e to the power of x, and this gives you itself, e to the power of x times x to the power of 1/2. And this is it when it comes to calculus. And so what we do, we rewrite this as x to the power of positive 1/2 in the denominator, and it becomes a square root. Okay, so this goes down, becomes x to the power of positive 1/2, and we know that it's square root of x. At this point, you have to factor this as follows. And I went over the factoring. One is very simple, just take the common denominator. If you multiply this guy by 2 square root of x and put it at top, okay, in other words, in other words, and now this, you have to multiply it by the denominator. Now, again, there may be another step which is simple. You should be able to figure it out on your own. I did that for you. You use the quotient rule on this. The derivative of the top is itself times the bottom minus the bottom gives us just 1 times the top over the bottom squared. And now, again, you're done with calculus. You distribute. Remember that, I hope. And these two cancel each other, and you're done. Okay. These questions were done. Okay. I was most interested in this stuff that they were a little bit different in the practice test that student had a little bit of a difficulty with. You're multiplying 5x by 3x minus 2 to the power of 4. This uses the product rule in conjunction with the extended power rule or the chain rule, because 5x gives you 5 times 3x minus 2 to the power of 4. That is f prime g. F prime is 5. Now, what is g prime? What is the derivative of this one? You use the extended power rule. 4 sits in front, 3x minus 2 cubed, and then by the chain rule times 3 by the product rule times 5x. So notice what happens. I want to write this in case. So this is the f function. This is the g function. This is f prime. This is g plus g prime f. So this whole thing is a g prime. So I want you to see that. Now it's just a matter of factoring. Again, this was done for you. You should have no problem seeing the common factor is 5, also 3x minus 2, and you choose the smaller of the two, which is cube. As long as you see that step, let me just write that step at top. In other words, 5 is in common, 3x minus 2 is in common. This has exponent 4, this has exponent 3, and you're going to choose the smaller of the two. And that works out. And you simplify. In other words, quite a few steps of algebra, everybody. Quite a few steps. Okay. Here's the last question. You use the quotient rule, and because the denominator is a function of x, you use the chain rule as well. So combination of the two. So we are looking at this quotient rule first. The derivative of the top is 1 times the bottom minus. What is the derivative of the bottom? 4. Excuse me, times 2x minus 1 cubed, then times 2, and then times the top, which is x, over the bottom squared. Again, I want to write this for everybody, that if this is f and this is g, so this is f prime g, this whole thing. So this is minus, let's just, this whole thing is g prime. Okay, and that's the idea. As long as we can see this, we are in good shape. Now I'm going to simplify by factoring the 2x minus 1 cubed. Okay, everybody, 2x minus 1 cubed. So the first one gives you 2x minus 1, and the next one gives you minus 4 times 2x, which is minus 8x. All you have to do, simplify the top. This becomes negative 6x minus 1, and 2x minus 1 cubed goes away and changes this to number 5. And that's your final answer, everybody. That's your final answer.